Hello everyone and welcome to the last lecture here at the Brazilian ICPC summer school. Well, as you can see right now here on the blackboard, the lecture today is about mixed topics because well, basically I wanted to talk about so many things that did not deserve having its own lecture by each one of them by themselves, so I put them all together at the end in a single lecture. So I hope you liked it. Okay, I hope you will like this lecture, and let's start. Well, the first thing we will see is a very simple principle, but it's important to keep in mind, and it's that you should improve your algorithm first. Almost always, this will be more important and will give you better gains more quickly, faster than before micro-tuning the algorithm. What do I mean by micro-tuning? Improving the basic operations of the algorithm instead of the algorithm by itself. Like, I don't know, this would be a very simple example of what I mean. Maybe you are only adding numbers, not multiplying, so you know that you don't go a lot over the modulus, just to keep it again, instead of doing just the full modulus to put it back in range. You might just subtract when you're above the modulus, so you avoid a division. This might be especially much cheaper when the modulus is not a constant but is unknown, because that case is like the much more expensive case of the division. Well, this is the kind of thing that I mean by micro-tuning, starting to change the algorithm. And this is much more error prone. For example, if you do this and then, but again, you're multiplying x before instead of just adding things. If you just forget to subtract after one single addition, maybe you're too far away and one subtraction won't do, and it's already wrong answer. Or if you multiply, it's probably this does not work. So it's much more error prone, and sometimes you test it and the gain is minimal or irrelevant, because it's hard to get a lot of progress with these kinds of idea, and it's not so obvious that they will be better. Sometimes changes like this, because the compiler already optimizes a lot, change nothing basically. But rarely the compiler can optimize your algorithm, and you can. And well, of course, this means using linear time algorithms instead of quadratic and things like that. But I don't only mean asymptotic complexity. I also mean improving the constant. In terms of improving constant time, not constant time, but the constant of your running time, it is also usually more important to improve the algorithm, even by a constant, before micro-tuning. I will give you a real example. I was doing a live stream, actually, trying to solve a Hamiltonian flights problem at the judge CSES online. It's a very well-known judge, very nice for practice. And this problem is a very standard dynamic programming problem. Literally, you have to count how many paths there are in a graph from A to B. I think it was directed, but it doesn't matter. So you just have to count how many paths from A to B, literally. So standard dynamic programming algorithm, very similar to simple paths. Yeah, of course. I forgot to say they should be simple paths. So yeah, it's similar to the standard Hamiltonian cycle or path dynamic programming algorithm. With this complexity, you use a mask, like, okay, dp, I want to reach this node with a certain mask. In how many ways can I do that, or anything similar to that? There are different ways. We will see that soon. Yeah, okay, and of course the transition is choosing to what node j to go next. So this is the complexity easy, but it was giving me time limit, and well, after tuning and micro-tuning the algorithm a lot, and doing changes like this and many others, and changing the order of the ifs and micro optimizations, quite ugly, I managed to get it running like barely, like maybe, I don't know, I had 1 second and it took 0.95, like very barely I managed to get it to work, and okay, great. I knew that they weren't expecting something better than this, but my algorithm was already quite fast, so I mean, it was quite optimized, the details of the implementation, so I thought, oh, what am I doing wrong? And I went to see some other people's code, and I spotted like a trivial change where I could have divided my runtime by 4 immediately, no matter how I implemented the details. Just by changing the actual algorithm, I could have divided by 4 the runtime, which in this case was enough because I was like a bit above 1 second. So dividing by 4 my time would get me like 0.3 maybe. I don't know. I tested it and it was like, okay, now I am comfortable within the allowed time. And what was the detail? Well, just thinking about what masks are actually relevant. I tried all the 2 to the power of n masks, but here we have to go from A to B. So actually you can start with the bit for A already set, or you can ignore it, whatever, but the fact that the bit for node A is 0 or 1 gives no information, no relevant information, because you have no choice. You start at A, so you will have already visited A on the first step. You don't have to try both options. They are not useful. It's not like for any intermediate mask, it is relevant to check this state and also this state. No, because this one doesn't have sense. Doesn't make sense. You have to have started there. And the same happens for basically for the ending. If you already visited the ending, but not all the other nodes, then you lose. That is not a Hamiltonian path, which is I said simple path maybe, but again, the title says Hamiltonian. You have to count the number of Hamiltonian paths, actually. So in this problem, those masks immediately don't make sense. You don't have to compute that many. So you can basically ignore these 2 bits, assuming that you only use the interesting ones. Or even you can put an if and a break in your algorithm and avoid paying the n² part for those irrelevant masks, because only a single 2 to the power of n is very cheap. The problem is multiplying by n². So just with that detail, since you avoid this bit and this bit, your masks are 2 to the n-2 total. So your algorithm is 4 times faster, no matter how you implement it. I mean, it will do that 4 times less operations in total. So it was both easier and more relevant to the runtime. The impact was much more direct. So I think I learned the lesson, I hope, and I think this was a great example and a real example of where to put your attention at first. Maybe if you try to optimize the algorithm and you say, oh, okay, I cannot even get a divided by 2, nothing, because sometimes in backtracking and things like that, you can get an immediate divided by 2 just by using the symmetry of the board. Sometimes that happens. It depends on the problem. Okay, that was our first topic. Now we'll go to the second one, binary search in doubles. I just want to mention a little trick. It's not so important, but it's nice, so I want to mention it. Let's say you are doing binary search in a problem with doubles, so you're operating with doubles, and okay, you have no clue because the answer might be very huge or very small. This is an extreme number, but I just want to make I just want to give you a clear example. Okay, let's say the answer is 3, and you start with A and B bounds for your binary search at 1 and 10 to the 50. Okay, great. If you use the standard normal binary search where you split in the middle, A plus B divided by 2, then notice that since the answer is so small, you will first try in the middle, which is this divided by 2, and of course it will be lower, so you'll go to this divided by 4. Actually, you have to add 1, but 1 is so small that in doubles it will be ignored, actually, and you will be just dividing this by 2. Okay, so you will basically be dividing by 2 each step. And so you will take quite a lot to get close to 1. Basically, you will need the logarithm of this, which is like 50 times the log of 10. So that is more or less like 150, more than 150 steps to get to the answer for this double binary search. But this is unintuitive because if you're working with double, say, double has only 64 bits. And we know that binary search should get 1 bit of information per question. We're not doing an efficient question. We're not splitting evenly. And that is because when you're in integers, choosing the number in the middle actually splits in the middle the options. But with doubles, because there are the large doubles are farther apart. They are farther on the number line. They grow like this. The smallest ones are more concentrated. When you split in the middle, you're not splitting actually in the middle in terms of numbers of doubles. And so you can use this trick, which will get you faster convergence in this kind of case. Basically, if B is quite larger than A, more than twice A, then instead of using the arithmetic mean, use the geometric mean. Because this is like taking the midpoint in the exponent. Like, I don't know, if I am in 10 to the 10 and 10 to the 50, if you make this operation, that will give you 10 to the 30. So it's taking the mean of the exponents. So this will first get to the exponent in order to quickly get to the exponent to be correct. And once you have the exponent correct, which more or less is this condition, because the exponent is in binary, well, then you can do the normal one. So this will be faster. And this is basically guaranteed to arrive at the maximum precision of double. So it will give you the full precision of double in 64 bits, no matter what you're doing. It will always extract 1 bit extra per query. For example, many problems ask you to get 10 to the minus 9 relative error of precision, and that will always be achieved in like 40 steps. Of course, if your initial range is much smaller, you can get less than that, and even this will be fine. In fact, because of this, if the numbers are already close, like between 1 and 2, then okay, you know that the exponent is already basically correct, and so you don't need this first part. But this is an interesting trick because it can avoid you in some extreme cases to waste a lot of time. So I mean, maybe if we go from like 40 iterations maybe to more than 150, this runs 4 times faster. So it's good to know. Yeah, so basically this is it. And a detail, I am assuming that both A and B are positive to start with. So maybe if you want to put A to 0 for this kind of problems, well, if you are using doubles as a result, you probably want to start it actually at epsilon and not just 0. Because if you put an actual 0, then C will always be at 0, and this is broken. So this method assumes that you're already working with positive numbers. Next, I want to show you one very powerful trick that I call Fubini Trick, basically. Well, what is Fubini Trick? Well, it's named like that because of Fubini's theorem. Fubini's theorem is a well-known theorem in calculus. Basically, if you have an area like this, a rectangle in 2D, and you want to integrate a function over that rectangle, what you can do actually is forget that this is a rectangle, or maybe like slice it into well, like single dimensional slices. Here I took them vertical for some reason, and zoom over each vertical slice. And each slice over which you zoom will be a zoom in the other direction. And of course, I am saying zooms, but in the analysis version, these are integrals, which are like zooms of infinitely many very thin slices. So yeah, this is it. But basically, if we take an integrate operator that takes, integrate from A to B, this function, what Fubini tells you basically is that to do the 2D integration, you can do the integration of the integration of f. But one integration is in one dimension and the other is in the other dimension. And actually, Fubini theorem, the full version, says that you can swap this and the order doesn't change, because it's like zooming over the rows or zooming over the columns. It's the same idea. Well, there are hypotheses that f must be a nice function, but basically this is the idea. And if instead of a function we have a rectangle, well, that's our case, and the idea is the same. The idea is exactly the same. And this might be a general matrix in 3D, 4D, 5D, whatever dimensions we have. It is very common to have to compute this value, basically, that you have a matrix with data, with numbers, whatever they are. And for each value, say this value in the matrix, I want to compute the sum of all of this, which algebraically would be the sum of all cells having indices. If I index the columns and rows in the matrix, I want the sum of all cells that have indices at most the ones of this cell. So those whose indices are obtained by reducing the indices of this cell. If I had chosen this one, I want the sum of all of this. because in x you have 1, so you can choose 0 or 1 for x, and in y you have up to 4. You have 4 here, so you can choose up to 0, 1, and 4. So always these rectangles. And the same in 3D, the same. If you want the sum of x, y, z, well, you will have to sum all x prime, y prime, z prime, having x prime lower than x, y prime lower than y, and z prime lower than z. Sorry, lower or equal. That's the definition I am using because it's easier to code, basically. We will see the trick to code it efficiently. And well, Fubini's theorem tells us that actually we can do it in 2 steps. Remember, we can first do the integral in 1 dimension, and I can change basically integral to sum, and it's the same because basically that's the same idea. And then over that result, I take that result, and that is what I am going to sum in the other direction. So, for example, let's say that first I make one pass summing in 1 dimension over the rows. Well, summing in 1 dimension is just computing the prefix sum, the normal prefix sum in 1 dimension function. So in this cell, I will have the sum of all of these ones. In this cell, I will have the sum of all of these ones, and so on. I make 1 4. I can make one single 4 going like this through all the matrix. And when I see one element, I sum the one on its left because I want to do it in place. It's easy and efficient to implement in place, this thing. Okay. But essentially, I can do it all together, but it's like each row is independent. I am just doing the prefix sum in place. Very standard algorithm. Well, just by looking at this drawing, when you finish, you can clearly see that, oh, if now I take that result and I decide to sum it vertically with the same idea, the same algorithm, but going vertically like this, and when I am on one element, I sum the one that is on top of it in place. Well, I will get the prefix sum in vertical, but then this one will sum all of these ones, and since those are already the sum over the rows, well, I finally get exactly what I wanted. So that is very nice. And well, this maps to very nice code that you can actually do in any number of dimensions. Here I have the code for you. And well, maybe I can zoom it a bit. Oh, I broke everything by zooming. But yeah, this is a general way to do it in many dimensions. Like this is an example code for 5 dimensions. And of course, if you have 5 dimensions, you won't copy paste 5 times that code. You don't want to do that. You want to actually do a 4 over the dimensions because you have 5 dimensions. So 2 or more, use a 4. Here is a 4 in the dimensions, and then you go through all the matrix. This would be the indices A, B, C, D, E. And then we compute, taking into account the variable dim, what are the indices that we have to reduce. So basically, we will have to do A, B, C, D, E, but one of those indices I have to reduce by 1 because I want to look at the left one, the top one, etc. Exactly 1, depending on which dimension I'm looking now, I have to reduce by 1. Well, and of course I check if that previous is in the matrix, because basically, for example, if I'm in the first tape going to the left, well, this one is not modified. I skip it, but it's easier in the code to just put an if and I say, okay, if I have someone to the left, just add that one in place. So this is super simple for any number of dimensions, but really powerful and very efficient, and it operates in place. So also it uses very little memory, and that makes it even more efficient. So yeah, I hope you like this trick, and I want to show more examples where this trick comes up very nicely. And well, it's exactly the same, but maybe it's not obvious that it's the same. And the first example I want to give is the case of a divisor clause set. That is a set like this one on the left that I have in Fuchsia and Magenta. In Magenta here I have numbers, and they are closed by divisor set. That means that whenever you have a number like 50, you have all the divisors. Here you have 10, you have 2, you have 25, etc. You have all the divisors of this number. Okay, that is what it means. Well, what's the use? So you can imagine that this any set that has this property, you can actually imagine like it forms a table. And here, well, the last rows are missing, but if they were not missing, this would be the number 4 times 25, 100, etc. But okay, some are missing. Better, we have to compute less, no problem. But to us, this is like 2D matrix. Why is it like a 2D matrix? Well, because there are two primes, prime 2 and prime 5. If our divisor clause set has more primes appearing, well, it's like a multi-dimensional matrix. And it might be, if there are 1,000 primes, well, this might be a 1,000 dimension matrix. But we actually don't care because we don't use the full matrix. We only care about those cells that appear, so we're fine. Well, let's say you want to compute, let's say like that, like here, each number comes with some value. So 10 actually has value 3, 20 has value 4, however you got those numbers in your algorithm. Well, and now you need to compute, to finish the problem, for each number, the sum of the value over all the divisors. Well, luckily, based on the way you arrange them on the table, because basically, I never said it, but the way to arrange it is that you have one dimension per prime, and in that dimension you put the powers of the prime, like these are the powers of 2, well, this is actually the first column of the table, and then for the prime 5 you have the powers of 5, and so on. And in each cell you put the product corresponding to that. So the coordinates, if I were to actually put the coordinates here, the coordinates in each dimension tell you the exponent to that prime. And well, if you do it like this, then you can see that the area that we want to sum for each number is exactly the sum matrix that we have been learning how to sum. So you can do it, but I want to emphasize that you don't have to actually create a matrix in memory to use this algorithm. You don't need it, because remember our code. In essence, essentially our code is, okay, you've seen that you have the Fubini pattern, okay, then you want to sum your matrix. Well, just do a 4 in the dimension, and for each dimension what you have to do is this part, but this part is not essential that you do it in a matrix, the second part. These 5 fours actually could just be written as a single 4 that says iterate over all cells. Well, the detail is that you have to go like in order, right? From lower indexes to larger indexes. But with that in mind, you can do a 4 over all cells. That's basically the idea. And for each cell, all you have to do is, well, if it has a predecessor cell according to the current dimension that you're doing this step, sum it in place. That's all. Well, you can do that easily, even if you don't do a matrix algorithm. Basically, let's say you have the numbers here, and these are the values, and you have them in an array, and they are sorted numerically, because that's easy. That's calling sort function. Well, no problem. You can go from lower to larger, because numerical sorting goes in a strange order, but that strange order respects that the indices grow. So you will see the predecessor. You will have the predecessor before. So even if you go in a strange order, since the rows and the columns are independent on each step, it's no problem. The method works the same. So you can go one for each one. Let's say I start doing dimension 2. I have to do both dimension. This one is 2-dimensional, luckily, in any order. If I have many primes, I should do one iteration for each prime. And in each iteration, I just check the numbers that are a multiple of that prime, because that means that they are not like the first column, for example, and have a predecessor. And I have to sum anything that divides them. So if I am doing 2 first, okay, I will go 1, stays the same, 2. I have to add 1, which is the predecessor, so I get 4. 4, the predecessor is 2, so I get 6. 5 doesn't have predecessor. 8, I have to add 4, which now has 6, so I get 8. 10, I have to add 5, now I get 4. 20, I have to add 10, now I get 8. I might do the calculations wrong, but okay, I'll try my best. Good, we're done. We did the step for 2. Now we have to do the iteration with 5, which is like going in this direction. I did it in this direction, the accumulation. So you can check that, for example, 8 now has a values of 8, which is correctly the sum of all of these, and 10, for example, has a value of 4, which is the sum of all of this. So I have the sums vertically done. And if now I accumulate horizontally, that will do. But that is just checking those that are divisible by 5 and adding. So 1 is not, 2 is not, this one doesn't change. 5 is divisible by 5. I have to add the predecessor, which is 1, because just I am using that just dividing by 5 will give me the one on the left, and dividing by 2 gives me the one on the top. I divide by 5, I add, I get 2. 10, I have to add 5, I get 6. 20, I have to add 10, I get 14. 25 is, oh, I'm dividing by 2. I should be dividing by 5. This one was correct, but this one I have to add 2 is 8. And 20, I have to add 4, it's 14. And 25, I have to add 5, it's 7. And 50, I have to add 10, it's 50. Okay, if I didn't do the calculation wrong, which is highly likely that I did something wrong, this should be the sum for each one of the values of the divisors. Let's check. The divisors of 50 are these ones, and the sum of values is actually 15, and here I have 15. Oh, great, this one worked. Maybe 10 works too. 10 has to have 8 and has 8. Okay, it seems like it worked, and well, this idea is very powerful. And you see that the complexity is just p, the number of different primes, not divisors. There is nothing proportional to divisors here. Basically, it's just primes times the total numbers. Of course, the divisors are implicit in the fact that the set is divisor closed. It's never missing a divisor, but it's simply total numbers times the number of different primes, which is 2 here. So it's super, super fast. And the implementation is easy and efficient. Here I have, where do I have it? Here. Here I have a scheme for this. Basically, for each prime, you go, you check each number from lower to larger. If the number is divisible by the prime, you add in place the number divided by the prime. That I showed. So super easy. But you see this, if you see this without knowing the theory, maybe you say, oh, why does that algorithm work? It's magic. And no, it's not magic. It's just adding in 2D. So it's just doing the Fubini trick, but remembering, but the matrix is like imaginary. It's in our minds. In the code, you just have an array and know how to go up and left. And of course, if there are more primes, like in this code, it's the same. You do a 4 in the primes, and that's like doing a 4 in the dimensions. But this is very, very efficient. And finally, as a final example of this, I want to show one great example which I like a lot, and that is, okay, let's say you have a matrix, but in many dimensions, and actually it is in n dimensions. Your matrix is size 2 times 2 times 2 times 2. So the indexes, then, in that case, this is called a hypercube. The indices are just 0 or 1. You can index your matrix like 0, 1, 0, 0, 1, no other option. So that's basically a bit mask. So that's like saying, okay, if each of those has a value, then basically that's saying like, okay, I have many bit masks, maybe all the bit masks, the 2 to the power of n bit mask, and each of them has a certain value that I'm interested in, and somehow I got it. And now what I need is to sum, let's say you want to sum for each bit mask, which represents a set, the sum of the values of all the subsets. Well, it's easy to check now that the subsets are exactly in terms of the matrix, of the large dimensional matrix, which is 2 by 2 by 2, the subsets are just choosing some ones and changing to zeros. So the subsets are those that you get when you do this operation of adding the submatrix. So you can use the code that we already learned. You go through each dimensions, which is each bit, and you iterate, and for every element, if it's a 1, basically you add in place the same mask but with a 0. Because since each row is dimension 2, doing the prefix sum is trivial. It's okay, to the right one, add the left one, which is well, of course, that is done in many dimensions, so the matrix is huge, it's 2 to the power of n, but for each number you do a very simple thing. You add one other value, and so the code is very short and very where do I have it? Here I have it. The code is very short and very efficient, like this. Here is the full code to this idea. You just iterate through all the bits. And for each bit, okay, iterate all the matrix, and the matrix here is actually all the masks. And for each mask, well, if it has the bit set, just add to that one the same with the bit of. So super efficient code. If you see it, you think it's black magic, and the complexity is super fast. It's just n, the number of just n times 2 to the power of n. super efficient algorithm. Maybe you know how to solve this problem in this complexity, but maybe the way that you knew was more complicated. Well, now you know a very simple way. Okay, now I want to talk about 4 ways to implement a dynamic programming algorithm for the same problem. So in principle, for each problem, you have like 4 ways to make the dynamic programming algorithm for it. At least in principle. So let's see. Let's go directly to our example. One of the most well-known basic dynamic programming algorithms problems. Let's say you want to go from A to B in a matrix, and you can only move to the right and down, right or down, only directions. And there are some cells which I mark white, which are like the penalty. Let's say. Those cells have a penalty and the others are free, or maybe they have a number with how much they pay. It doesn't matter. Here I say Mij would be the cost of that cell, whether maybe it's 1 if it has penalty, 0 if it's free. It doesn't matter. I want the cheapest path to be. That's the basic idea. Well, I assume that you know how to solve this one. It's easy. So yeah, there are at least 2 ways to make the recursion. If you're going to use dynamic programming, you have a recursion somewhere, a recursive function. And here I created 2 versions, F1 and F2 for this problem. So we already have 2 versions. Basically, what does each one of them compute? So if you look, F1 goes to +1, +1, and F2 goes -1, -1. Based on this, you might guess the semantics of these functions, which is critical. When you do an algorithm like this, you have to think, what does it mean, F1 of Ij? Because actually the part on the right, I cannot write it without knowing first what I want to compute. You might reverse engineer and looking at this guess what this computes, but the normal process is the reverse. You say, okay, I want to compute this. What formula do I use? Based on this, F1 is actually computing for each cell. Let's say I look at the value F1 of this cell. Well, F1 is actually computing from all the possible paths that start in this cell and get to B. What's the minimum cost? So what's the minimum cost from this cell to B? The optimum is what this function F1 computes. And what does it compute F1 here? Well, F1 here will compute the optimum path to B. And that's it. So if you compute F1, you will get for each cell in the matrix, the optimum path from there to B. If you compute the other one, F2, what you're actually computing is for each cell in the matrix, the optimum path from the start A to that cell. So here the graph is very symmetric, so it seems like completely the same. But note that they are not equivalent. They are not actually equivalent because let's see, for example, the answer is a different number, and if you only want the answer, you can use any of these and it's the same. It will be interchangeable to you, but they will not be the same if you're interested in all the numbers, and maybe you need them because maybe the problem asks, or maybe you want to do something else and this is just a pre-computation, so maybe you need all of the numbers. And if you need them all, you cannot just interchange them. I mean, you might need one of these values and not the other. So you have to think, okay, which one do I need? So the problem, let's say, for example, the output of the problem is actually function F2. The output of the problem is for each cell, tell me the optimum way to go from A to that cell. Then you cannot compute this one. That would be wrong. And also, for example, maybe the problem says, okay, I want from all the minimum path, I want you to output the lexicographically smallest one. Then also, only one of these two will be useful to compute that, because basically the way to compute the lexicographically minimum one is that whenever you have both options in the path, if you go greedily constructing the path from the first direction in the path to the last one in order, whenever you have a choice such that both options produce the optimal when you do the calculation, you choose greedily the smallest one. But you have to have computed the values in such a way that they are compatible with the order. So if the path is going to be like, okay, right, 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 and the output goes right, 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 and I want the lexicographically minimum, then I can only use F1. F2 will be useless for that, because basically I will want to say, okay, if I start from this cell and go to B, can I get the minimum? Or have I already ruined everything? If I go to this cell and go to B, can I get the minimum? Or will I have already ruined everything? And you basically don't have that information if you compute F2. If you compute F2, here you will have the information of going from A to here, but that's not what you need in order to do lexicographically minimum. So you have to carefully choose which one. And again, I emphasize that here the graph is so symmetric that they are very similar, but they might actually be more different than this. And this is the most important difference, the first one, whether you go basically forward or backward. And I want to emphasize that you might only be able to solve the problem with one of these two. So it's worth being aware of this difference in order to try to think, okay, maybe I should put the arrows the other way. Let me think again. Because I've seen many cases where a student almost has the solution. I've seen it many times. The student almost has the solution, but he's like thinking of the arrows in the wrong direction. As soon as the arrows will be flipped, the problem will actually be solved. But with the arrows like they are, and also it's sad when you don't think about this and code all the problem, and then suddenly you realize, oh, I needed the lexicographically smallest one. Then how I have to put the arrows? Oh, the arrows are in the wrong direction. You have to change everything. That's bad. So think of this from the beginning. And here I have drawn actually the recursion calls. And if you see in order to compute this cell, the function f2 will need these two marked subproblems to be pre-computed before in order to use them, and the function f1 uses this one. So that might be a heuristic in order to remember which one to use. There's a bit of personal preference. I tend to think always in this way, like f1 way, because that way the arrows of the calls, the definition of the problem might be reversed, because it's like, okay, from here to the ending instead of the typical from the start to where I am. But the arrows of the calls are magically in the direction that I walk in the problem, and that for minimum path problems tends to be better for thinking. But again, I emphasize, you might need to look what the problem asks you. Even if the path is written this way and it's not symmetric and anything, maybe the problem actually asks you to compute each value, and each value has to have the best way to get from the start to there. And if you need that, well, you have to do this one. The other one doesn't work. Okay, good, enough talking. But that gives us two ways to do dynamic programming. What is the other two? Well, basically there is a trick in order to reverse the arrows. Or well, another way to implement it. Now, this difference is more important because it changes the formula, and it actually changes the output. It changes what values you're going to get. You will get a different output matrix, and the subproblems will have different results and different numbers and will mean different things if you change this. But there are, for each of these one, there are two ways to compute it, which will get to the same number. So in that sense, they are more or less equivalent. But that will give us the 4 ways in total, 2 for each of these. And what are those 2 ways to compute? Well, one is to actually do the standard recursion, either bottom up or with memoization and recursion, but to do the normal recursion where when you are standing on ij, you in order to compute it, you already have the values of all its subproblems. And now that you have the values of all the subproblems, you put the code that computes Fij. And you compute it using all the values. That's the more classical way. But there is another way to implement it, because in a lot of problems, it depends on the problem. If you need to have all the values there at once, it's hard to do it. But you could in principle, actually. Basically, in many cases, it's like this. You have to actually use an accumulating function. And basically, it's an associative function like the minimum, and you have to accumulate over all the possible children in the call, in the recursion call. So instead of going, standing on a cell and saying, okay, for each, let's say I'm doing F1, okay, for each of my children that I need, I will check its value and take the minimum of those. Well, instead of that, I initialize each cell with whatever value is useful for my problem. Maybe here, since I'm taking minimum, I will initialize everything to plus infinity. And then do the opposite way, so that when I reach a cell, its value is already computed. And but what do I have to do? Well, then the workers have to be the children, not the parent. And what you do is you go in the reverse way, and whenever you're standing on a node, you say, okay, I have my value now. Maybe here you have to do an adjustment and add the value once you arrive, but you will have the value and say, okay, now I will push this value to all my parents in the recursion. So when you're standing in Fij plus 1, you would actually push your value to the parent Fij. And you would accumulate, let's say let's say Fij, which is this one, was still plus infinity. When you are standing now here and you say, oh, okay, this one is, I don't know, 5. I will push it and now check and accumulate. Oh, 5 is better, so I change. Then the algorithm continues, and when you're standing here, which is the other element, you say, oh, I found a 4, so I will push to the parent. And you check, oh, okay, it's better, so it changes, and this one has gone from 5 to 4. And when you actually reach the cell Aij, you already have the minimum there. And so the problem is already solved here. But what you now have to do, well, maybe you have to add this, but that's a single step. And then what you have to do, since your problem is solved, is to push it to your parents, and so on. So instead of standing on a parent, so to speak, and call all the children and get the values and see what happens and make the calculation in the parent, like the work is done by the children updating and pushing the value to the parents. So that has the practical effect. That in the code, even if your arrows, let's say you're computing F1, so your arrows in the recursion are like this. The dependency is that you need these values to be ready for this one to be complete. But when you're actually pushing values in this implementation, the arrows that you will use are the reverse one, because are the arrows from the children to the parent that you have to push and update the values. But the values that you're computing do not change. I don't know if you see it, but basically the idea is that you're getting the arrows like in the other case, but you're keeping the same values in the table. And remember, the values in the table, you might get to choose any one sometimes, but in many problems you cannot choose them. The problem needs one, and only one of these tables will work, because you need lexicographical minimum, or because you need those values, or whatever. But the trick of doing a push instead of normal, let's say, instead of normal recursion, pushing the value and updating it from the children to the parent, has the effect of allowing you to reverse the arrows in the code. And why that might be useful? Well, that's an excellent question. So basically, this is like, instead of having graph G, if G is the graph of recursion calls from the states, you can operate in the transpose graph with the arrows backwards. Why might that be useful? Well, because sometimes computing the transpose of the graph with the arrows in the other direction is much easier. And when that happens, you can use the push one. And we know an example of that already. And that's basically the idea of the sieve of Eratosthenes for the primes. Let's say, for example, you have to compute for each number in the entire numbers, like 10, you have to compute the sum of the divisors. Like 10 would be 1, 2, 5, those would be the divisors, and you will need to compute that. Well, the natural algorithm is just dynamic programming. You say, okay, the function for n is the sum of the divisors of n of, n actually. It doesn't even have a recursion. It's like everything is base case, but you need the divisors, right? An example with an actual recursion might be phi. You can compute the function phi of n using a very well-known recursion that phi of n is n minus phi on the divisors. So with this one, you can actually see a code where you would actually like to do dynamic programming going to the divisors. But going from a number to the divisors is hard. And basically this one, you cannot easily change the formula because here you want to compute phi, so the values that you want to compute is phi, and phi is given by this recursion, so you cannot easily choose another recursion and swap the arrows. You have to compute this one. It's not like you have the option of changing from f1 to f2. Yeah, the problem is fixing this function for you. But you can change that by using the push trick. Instead of going through each number and for that number trying to find the divisors, which is hard, you have to factor or do something complicated, you do the other way around. Here you need the sum, so what you would basically do, but you know that the answer will be n minus. So if you want to compute phi, you basically start the array with each number having its own value, so 10 would have 10 and 5 would have 5. And you go through all the numbers, and generating the divisors of a number is hard, but generating the arrows in their direction is just the multiples. And the multiples is very easy to do. It's like normal sieve. And so that's the trick. You go number by number and you go to the multiples and you push the values in order to go updating. And here pushing the values is just subtracting my phi. So if phi of 5 is, I don't know, 4, when I do this, I will go through all the multiples and to all of them subtract 4. And when I get to 10, instead of 10, I will have already subtracted phi of 4, which is so 6, but I would have also subtracted phi of 1, which is 1, and phi of 2, which is 1, so I would get 4. And I have no idea, maybe that's correct. Yeah, I think phi of 10 should be 4. So yeah, I have the correct value, and I can push it to the multiples of 10, and so on. So, and this will be n log n time, very efficient. If you had to factor, it would be much harder. Another example where this shines is there is a well-known problem where like the solution is n cube, and what you have to do is it's like this, longest increasing subsequence, but you have to produce two increasing subsequences, so you can paint in black or white, let's say black or yellow, white or yellow, or you can leave unpainted, but the white one has to be increasing the white one has to be increasing subsequence, let's say, and the other one has to be decreasing, just because the problem says so. And those that you leave unpainted, no restriction. But you want to paint as many as possible. It doesn't matter which color, but you have to paint as many as possible. So the main idea is just, have a dynamic programming algorithm and remember in the state, well, the last white I used was this one, the last yellow I used was this one. And in general, in the algorithm, I am looking at the numbers, and the next number to check is k. Okay, but with this meaning, you can take any of these two conventions. You can do the f1 way or the f2 way. You might ask, going from the start to this situation and putting numbers one by one, let's say you go from left to right putting numbers, in case which number is the last one you put, and this is just the state in order to remember which was the last white or the last yellow you used, because that allows you to tell when you use a number and choose its color, if you're keeping the restriction that you're growing one sequence and the other one is descending. If you choose that this means from the beginning where I didn't put anything and I've grown and k is the last number that I considered, maybe I put it, maybe I didn't, but this is the last one that I considered. What is the maximum that I can paint? That is a state that is tricky to compute. Well, that corresponds here to something more similar to the f2 way, I think. And it's harder to compute because, and it's not so obvious that it works in n cube time. It does, but it's not so obvious. And the graph is uglier, let's say, because from this situation you have to check, I have k is the last one that I put, so I have to do what I did with k, but that depends on I and j. If I equals k, then I know I painted it white, and the previous state must have had another different node in white. The previous state must have been of the form I prime, the same j, and k minus 1. So I have to check all the possible values of I prime, which are all the lower than k, but they must not be I and they must not be J, because that doesn't work, obviously. In fact, they must be lower than J, because lower than I and different to J. So there are a lot of restrictions. It's more complicated, and from each of state there is at most n possible other states. So it's obviously O n fourth, and it's not so immediately obvious that this is actually n squared. It's n cube. Sorry, it is n cube because actually for most states k is larger than I and j. It's not equal to any of these, and so the only possibility is that you didn't choose that number, and so the only state to which you go is I, j, k minus 1. But this is all more complicated. I believe that in this problem everything is much simpler, much clearer, less bug prone if you just take this direction, where you say, okay, the current situation, the current place that I'm standing is that I is the last white I used, j is the last yellow I used, and k is the last number I looked at. So of course k will be larger than I and j or equal. From here on to the end, what is the best I can do? Those that I already painted, I don't care. I only want to count painting from now to the future. What is the most I can paint? And so here, obviously, you will always move to k plus 1 because you will consider one more number. And you know that all you have to do is compare k plus 1 to the ith one, which is the last white, and seeing you can put it there. And that's the possibility of painting it white. And if you do, you move to basically k plus 1 or k, depending on your indices. Let's say k, j, k plus 1, possibly something like that. If you can use the yellow one because it descends, you would change it simply to I, k plus 1, and other ones you keep both and go to k plus 1. But it's only 3 options, and the transition is much easier and much clearer, and so it's obvious that this is n cube. And well, it makes sense that they have to, now that we have think about this in this abstract way, thinking about the graph of the recurrence and knowing about the push idea and everything, like, okay, it makes sense that they both take the same time because the number of arrows in the graph is the same. But that was not so obvious if we had only thought about the first version. And the code the transition had a lot more cases because I have to go backward, and the easy way is to go forward here. So I hope that I have raised awareness to you into this notion that maybe the two ways of thinking might be very different for a problem, and one might be much easier than the other. And well, this would be another example. This last case, we see that one way of the arrows is much easier to compute because every node has a degree 3 at most, basically, instead of having a lot of more chaotic previous nodes. But maybe because of the question the problem asks, it asks the lexicographically minimum in some weird sense, you get to the conclusion, oh no, I need the other one, the one that is ugly. Well, you might possibly use the trick of pushing to reverse the arrow, and so in the code you use the easy version, but the recursion that you're actually computing is the one that you need for the problem, even if the direct transitions are harder to code somewhat. Okay, now I want to show you quickly some amazing results about the Laplacian matrix of a graph that you might not know or you might know. Well, this is the Laplacian matrix of a graph or similar. What is this? Basically, you take a graph like this one. This is the complete graph with 4 nodes, and I've labeled all of the edges. A more organized way to label them might be, okay, instead of A, just E12, instead of B, I could have put E13, something like that, but okay, just to not complicate everything with indexes, I just said, okay, 1 letter per edge, and this is the way. So the thing on the right is the Laplacian matrix. You build it like this. If it's n nodes in the graph, it's n times n matrix. And what do you do? Well, basically, you put like this. For each, it's similar to the adjacency matrix in that at place ij, you will have the edge going from node I to node j. So if this is node 1, 2, 3, 4, 1, 2, 3, 4, you can see that, for example, 1, 3, I call it B, and we have at 1, 3, B, and this is symmetric at 3, 1, I also have B. But all the edges are negative. That's just because that's the definition. And in the diagonal, what do I have? Well, in the diagonal, you have all of the edges, but now zooming, positive, all of the edges of that node. So node 1 has A, B, C, so A plus B plus C. Node 3 has B plus D plus F, and node 3 has B plus D plus F. That's it. Why would I like such a matrix? Well, because magically the determinant of this matrix has a special property. Well, the determinant is always 0. So this matrix has determinant equal to 0. It is easy to check actually that all the columns sum to 0. So obviously this is not linearly independent, and thus it sums up to 0. So the determinant is 0. But if you remove any row and column, let's say for example I remove the last one, the last row and the last column. But for any I that I choose, if I remove the row I and the column I, always the same one. That's the trick. You have to remove one and remove the same column that as row, right? The easiest one is just remove the last one. And that's it. Well, this gives you a new matrix, one smaller, and the determinant of that is very interesting. It has a great property. Let's look at it with the help of Wolfram. Okay, it has a lot of terms. The determinant of this one, actually, it has how many terms does it have? Oh, I don't know. I think 16 terms. It should have 16 terms. Yeah, it has 16, and that is correct because 16 is the number of spanning trees in a graph of 4 nodes. There is a formula which can be proved using this matrix and calculating that a graph with n nodes, the complete graph of n nodes has n to the n minus 2 spanning trees. And what you will see is that each term in this ugly determinant, when you expand it completely, each term is exactly one spanning tree. For example, ACD appears here. Okay, what is ACD if I draw it? It's A, C, D. Okay, that is a valid spanning tree. Great. I don't know, take another one. ADF. Oh, ADF. Okay, that also is a spanning tree. And so on. Maybe we should have ABC. Yeah, the first term is ABC, which is a star, like this. And you can check that, for example, A, B, D will not appear among the terms because that is not a spanning tree and it is not here. So yeah, that is always happen. This was not at random. I will not prove it, but you can Google the proofs of these things. Later we will see the 2T matrix, and that has a very nice proof, the result. This one I think it's uglier, but maybe it also has a nice proof. But I will not show it. But you can know this property. And if you remember this, then it's easy to use it to your advantage. Because, okay, if you put general variables, this is very ugly. But now that you know the shape that this determinant has, well, each term is a spanning tree. So if instead of putting variables, you put actual numbers, like 0 if the edge doesn't exist, and 1 if the edge does exist in your specific graph, then what will be the result? Well, the matrix will be like the adjacency matrix, the normal adjacency matrix, but negative, except for the diagonal. In the diagonal, you put the degree, because now if you have 1 in the ones that exist and 0 in the other ones, this is just the degree of each node in the diagonal. It counts the edges. And okay, knowing that it always gives this expression, what will happen is that the determinant will be exactly the number of spanning trees in the graph. So you can count the number of spanning trees in any graph in n cube, very efficient, just computing the determinant. Because any term that has an edge that doesn't exist multiplies by 0 and disappears, and the other one remains. And also, if for some reason, I don't know why, but if for some reason you need to compute the sum of the weighted spanning tree, so each spanning tree, if the edges has weight, the weight of a spanning tree is the product of the weights, and you want the sum over all the spanning trees of the weight of the spanning tree. Well, this is exactly this determinant. The case of 0, 1 just counts them, but if you put weights, you can compute that. I don't know why you would like that, but basically this is the determinant, which is awesome. But this is not the only property of the Laplacian matrix. It has one more property. If instead of removing one Only one row and column. Let's say we pick, for example, two special nodes, 2 and 4. And so we choose these two, and we will destroy row and column 2 and row and column 4. So I destroy row and column 2, and I destroy row and column 4, because those are the two special nodes that I choose. So I get this smaller matrix, 2 by 2. And now what happens if I do the determinant of that one? Well, I get this with the help of Wolfram. And what is this? Here I have the graph as a helper. Okay, I will draw this set so that we can check experimentally. We have AB, and this is like this. We have a second term AD, and this is like this. We have AF, and this is like this. We have BC, and that is like this. We have BD, that is, BD is like this. Okay, good. BF is like this, and then we have CD, which is vertical like this, and then we have CF, awesome, like this. Is this correct? Yes, I think so. It seems so. And if you look at this and you guess what the pattern is, you might already be guessing. These are exactly all the spanning forest of two components, but such that this node is in one component and this is the node is in another component. There are only 8, and these are it. So basically, that always happens. This was not random. When you delete some chosen rows and columns for some nodes, well, the result will be each term of this general expression of determinant each term will correspond exactly to one spanning forest, having where the root of each tree in the forest is one of the special nodes, right? If we wanted to root them, but that is just to say that there are no two special nodes in the same forest, and there is one forest per node, right? These are all the possibilities. So if you want to count that, you can also use the same idea. You build a matrix, but you delete some rows strategically chosen, and you get this. So this is an awesome result. So I will put a link to Wikipedia on the web page of the Brazilian summer school, and there you can check, because there are more results about the Laplacian matrix in that page, and also it gives what you can do in the directed case and what it will give. It basically will count something related to directed trees. So I will now speak of the Tute matrix, which is another graph matrix, and this one is easier and has a very nice proof. I encourage you to think about the proof if you know something about determinants and permutations and that kind of thing, because the proof of this one is nice. Well, what is the Tute matrix? This one is more similar to the actual adjacency matrix. It's just like the one before. This is just like the one before, but basically you have zeros in the diagonal, so easier. And instead of having the same sign, well, this is symmetric, but you have different sign in the upper half, and in the lower half you have different signs. So why is this matrix useful? Well, basically, if you compute the determinant now and do the full expression, it doesn't count anything. It is not counting the number of things, not like before. That is not so nice. But there is a very interesting property. If this matrix is A, and this is for this graph, for example, well, as a polynomial in all these variables, right? The determinant will be 0 as a polynomial. So if you expand it and compute the actual polynomial, you will get 0 as a polynomial, nothing. Exactly if there is no perfect matching in the graph. So for this one over here, we should not get the 0 polynomial. And basically, you can check it, because if you know about permutations, the intuition is that when you choose, for example, this permutation AF, which corresponds to a matching, actually I can see it here. Well, the determinant for this will be something like minus a square, I think, minus f square, or maybe positive, not sure, but something like this. Well, the only way, so, sorry, the term that I'm choosing is, oh, so it minus minus, it gets positive. But it doesn't matter the sign. The thing is that it will be a square, f square. Basically, it says use this matching, a and f. Okay, nice. And there is no other way to choose two a's and two f's. So this monomial in the polynomial will not get killed with anything else. So as a polynomial, this is already non-zero once you have a perfect matching. What the thing that we must also check, and you can basically looking at permutations. Basically, if you have an odd permutation, it becomes 0, and if you have an even a permutation with all cycles even, then you have a matching. So then we go back to this case. So the expansion of this will give the 0 polynomial exactly when there are no perfect matches. Otherwise, it will be non-zero. Now the problem is that this is not such a nice condition, because if you actually have to test it as a polynomial, you put variables, and this is very expensive. So what do? Well, you put numbers instead. Oh, well, I never said this, but this is the construction for the full graph actually. But if your graph is lacking one edge is not there, then you replace it with 0. So this would be, that is similar to the previous case. We used the same idea. And now the result still holds, basically. Well, okay, since that edge cannot be used actually in a non-zero term, the basic idea is the same. But the thing is that here it is important that as a polynomial, this is 0 when there is no perfect matching. So you can use this trick to check for perfect matching in any graph, not only bipartite, any graph. This is amazing. Also, the complexity is great. It's n cube. The algorithm for testing for doing Gaussian elimination is super fast. Actually, it has very good constants. So this is a great result. Now, what do we do to test whether this is 0 as a polynomial quickly? We basically just put random variables, random values for each edge, because then we will have numbers, and we can do this polynomial, the computation, say mod p, mod 10 to the 9 plus 7, something like that, or maybe more. Maybe we can use 2 or 3 primes to be sure. And so we put random values and make computations modulo a big number. Of course, I don't put a random number for the edges that don't exist. Those are actually zeros. But for the variables corresponding to the edge, I choose random numbers. So I choose random, and b is 37. Okay, I put minus 37 here and 37 here, and so on for everything. And once I have numbers, I compute the determinant. If I don't get 0, then I am 100% sure that there is a perfect matching, because I know that if there is no perfect matching, this would be the 0 polynomial. So anything I replace will give it 0. But if I give 0, well, I must be really unlucky to have a chosen number such that by chance the result is 0, even though the polynomial is not 0. And there is a result that you can check. I will put the link in the web page, and you can check the link. There is a known inequality that basically proves how unlikely that is, and so you can test a few values and it will be fine. It will be really fast, especially if you use a large p. And what is more, this is to check if you have a perfect matching, but you can get the size of the maximum matching with this same technique, because actually you just have to check the rank of the matrix. Because basically, if you look carefully, when you delete one column and edge and row, you will get the matrix for a subgraph, basically. So if you look for the largest subgraph having a perfect matching, that will be the maximum matching, and that will have to have the same property. So the rank will be how many of those you can find linearly independent. So basically, the rank of the matrix will give you the size of the largest matching. So the algorithm is put random values, compute the matrix, compute the rank, and that's it. That will be the maximum. If you run it many times, you can take the maximum of the rank, just in case that some rows became linearly dependent by chance. But this is an extremely fast, very good algorithm to get maximum matching in a general arbitrary graph. Okay, now to continue, I want to discuss the case of polynomial interpolation at equally spaced points. So basically, you can assume if you have n equally spaced points that actually your points are 0, 1, n. I will do the calculations assuming that, but if there are other points, it's the same. The important critical thing is that they are equally spaced. So let's say you have a polynomial, you don't know the polynomial actually, but you know that it exists. But you have the values of the polynomial at 0, 1, up to n. So it's a polynomial of degree n. And your mission, your most basic mission might be to actually compute Pn plus 1, the next value. If you know how to jump one value, then in principle, repeating that many times, you could take these values and use it to jump one more, and so on. In principle, you could jump many values that way. But so how can we do it? There is a general way, which is the Lagrange interpolation polynomial. You probably know it. But okay, how do you use this? First, let me notice that in general, you can evaluate, you can use this expression to evaluate in O(n squared) time, basically. The general one, the only difference is that instead of using I here, this is actually xi, the points where I am evaluating, and here the ith point is actually just e, right? But in general, this is the only difference. So if you want to evaluate this polynomial in general, if you know the values, what you can do in order to evaluate at x, a particular value, you don't need to build the whole polynomial. You can just use this expression and run the code of this expression. Like, okay, I want to know the how much the polynomial value is at a certain x. Okay, I don't create the interpolating polynomial, but use this formula. I go and do a 4 with the summation and multiply by this, and do another 4 for the product and multiply by all this and divide by all this, and you will get it. And that will be time O(n squared). But also notice that if you want to actually get the polynomial itself, you can do it also in O(n squared) with the same formula. It's not too hard, because basically these numerators, okay, if you do it naively, just like this, the same, do the calculation, each of these products will have to be a polynomial product. And so you will have a polynomial maybe of size n, or on the order of n, and you multiply it by this, which only has 2 terms. Okay, it's easy, but that multiplication anyway takes order n. So maybe you say, that it's very expensive, because I have to do a lot of this one. So each of this one, if I multiply it from scratch, is n squared, and I have n, so it's n cubed. But all of these are almost the same if you check, because they multiply all the x minus j. Oh, sorry, when I say that only this changed, of course, here it's the same, x sub j. Okay, this is the only thing that changed in each case with each I is that I is excluded. So, for example, for 3 numbers, you have x minus x0, x minus x1, x minus x2. And for the first term, you exclude this one. For the second term, you exclude this one. And for the third term, you exclude this one. But then what you can do is you can compute this product, which you can do in n squared by just multiplying one by one. Each multiplication is linear time. And once you have the full product, you can use a Ruffini rule, which is just polynomial division, but it is easier for the case of just dividing by x minus something, to actually get the exact polynomial that you would get if you call this one p, let's say, from product. You can do Ruffini rule to do p divided by x minus I, and that will give you the one for the if step. But each of these one takes only n time, because Ruffini is so simple. Also, it's just normal polynomial division, but it's a rule for that case, which is easier to think mentally, but it's identical. It's isomorphic to a normal polynomial division. So yeah, that will be n squared time total, and you will get the final polynomial. So take that into account in case that is useful. But okay, let's say you don't want to, so that would be one approach. Actually do this calculation and evaluate it at n plus 1. And okay, you will get the net value in n squared time. But let's say we want to find a different way, a more elementary, because this feels too difficult, too powerful. Or maybe you don't want to do it modulo something, you want to do it, directly, I don't know. and you don't want to use doubles because that feels like will not have enough precision. So what can you do? Well, you can use an interesting way of thinking, and I think it's worth knowing this trick, is to remember that if you have a polynomial of degree n and you do px minus px plus 1, this will be a new polynomial, basically the difference polynomial. It's like the derivative, so to speak, because it looks at the differences. But this one will have degree n minus 1, so the degree will decrease by 1. Why? Well, basically because for each term, a polynomial is like a linear, has a sum of terms, and this is linear, so for each term, we basically just have to look at things of the form x to the n minus x plus 1 to the n. And then by Newton's binomial theorem, the leading term of this one will be x to the n, which is the same, and so cancels, and only another one remains, which is very similar to the proof that the derivative is n x times n minus 1, right? It's basically that's the leading term. So yeah, it's the same idea. Okay, how can that be useful? We can make this diagram and imagine that these are the values that you computed for the polynomial. Let's say it's degree 4 at 0, 1, 2, 3, 4. Okay, what do we do with that? We want to evaluate at 5, but let's suppose that we make another row, and just because we build the differences, 5 minus 3 to 10 minus 5, and so on. This would be minus 1, and it would be 1. I get the difference. Now, if this full rows corresponds to a certain polynomial of degree 4, because of what I just showed, these numbers must correspond to a polynomial, to the values of a polynomial of degree 3, another polynomial of degree 3. So this has degree 4, this has degree 3, and I can do it again, and of course the degree will decrease again. I will get one of degree 2. I can keep computing values. This will be degree 1. So I will get just numbers, and always the rule is very simple. I subtract this one minus this one. So this one is 3, this one is 6, no, 6, no, minus 6 actually. Yeah, okay. This one is 7, and so on. I can continue. 7 minus oh, like this. This is 13, I think. Okay, you get the idea. Okay, now what's the magic? The magic is that once you get down here, well, this one is degree 0, so you know that this one on the bottom is actually a constant polynomial, because you took the derivative so many times you got to a constant. Basically, this is the same intuition. So now you can be lazy and say, oh, since this is a constant, I can put 22 here, because if I actually these are you can imagine that this is actually a full table, right? It continues. There's no reason to stop. I do this like this just because I have the evaluation only at these points, but theoretically there is a polynomial and it has infinite evaluations, and here the rule would be the same. The evaluation here of the polynomial of degree 3 would actually be this minus this. So due to that, I can actually continue this to the right and also to the left, because I could use the same rule to the left, because once I went so down, I am sure that this is constant, and so it is very easy to extend. And then I can go backwards and use this extension to recompute these values, because since this is this minus this, well, each of these values is this plus this. You can check from this one is this plus this. Oh no, that's wrong. What did I do wrong? So this is the difference. So yeah, it should actually. Oh, this value is totally wrong. Okay, I miscalculated. Yeah, 10 minus 5, 9 minus 10. Yeah, these ones are correct. This one is correct. Yeah, this one is totally this is totally wrong. This should be, I guess, 2. So that this one is the sum. Okay, but you get the idea. Whatever the numbers are, this plus this will be this plus this will be this, and you can go up, and very quickly you get to the final number. So this is another algorithm that might be easier to remember and possibly easier. Yeah, I think it's easier to implement actually, and has a very nice intuition than the full formula, which is quite harder to get right. This is so simple and so nice. You can even use it by hand. And a very nice property that this one has and the other doesn't is that this is only using plus and minus. So this is awesome. This formula proves that when you have an x-spaced polynomial, you can get to the result with plus and minus only. At least if your evaluation is also equally spaced, right? Which was not obvious at all. So, for example, this proves that if you have in any field a polynomial with coefficients in any field, like the rationals, but magically you check at the degree plus 1 points consecutive and equally spaced, and then let's say in those integers you check, and it is always an integer, for example, or it is always in any subgroup of the field. Well, since you can get to the other values using only plus and minus, you won't leave the integers, you won't leave the subgroup, and so at all the integers, the evaluation will be guaranteed to still be integer, which is a nice result. You can solve one word final problem using that idea. Okay, so that's almost all. What else? Oh, no, I want to... Oh, two things to mention. First, basically this looks a lot like Pascal triangle, and so you can guess, this probably, actually if I want to write this directly as a linear combination of these values, because basically you can check that if you run this algorithm, but instead of using actual numbers, you start with variables there, like this is A, this is B, this is C, and you do the manipulation with the variables, you will get to here an expression, a linear expression in A, B, C, D, and the coefficients, well, will give you how to write the next value of the polynomial as a linear combination of the n plus 1 previous ones, right? Well, the coefficients will basically be the binomial coefficients. You can check that. I think they alternate signs, so it's like they are the binomial coefficients, but plus minus. You can experiment yourself, and yeah, basically that is not surprising because of this simple rule of adding like this and subtracting. Looks so similar to Pascal triangle that the combinatorial the binomial coefficients have to appear like, each value of this is this plus this, so it's the same recursion as Pascal triangle. Okay, what else? Oh, the final thing I want to mention is that you can be more general and more efficient than this, and you can actually do linear time interpolation for the special case, because we showed how to do quadratic general interpolation, and using FFT you can do general very fast interpolation, but this is a much more advanced complicated algorithm, especially if you need to use the division FFT. But basically for the special case of equally spaced, let's say use the same situation. You have the numbers at 0, 1 up to n, and you want to interpolate at those specific values, so no x, forget about x. We actually know that xy equals I, xi equals I. How can we interpolate quickly? Well, basically, if you want to, well, not interpolate, I don't want to give the full polynomial, but what I want to do is to evaluate at one specific point quickly. And we can do that in linear time. How? Well, basically, if you check, well, if that x happens to be one of the n plus 1 points, you know, it's all done. You just look at the result, you know it. So now we can assume that it is not one of those. So since this is not one of those, this product, which is all like the point I'm interested minus 0, the point I'm interested minus 1, up to the point I'm interested minus n, all of these terms are non-zero. So I can make this product like before, but now it's a number, not a polynomial, just a number. Call it p, and for the top, for each one I can just compute p divided by x minus I each time I need it, and again I can compute it very quickly. So I have to now find out how to quickly compute these denominators to solve the full problem. But that is easy because now they are just I minus j. So they are the consecutive integers, and look, if you draw them, they are like all equally spaced, but when you are at a certain I, you are iterating all the other values and multiplying by the difference. So so basically this is 1 multiplying because of this difference, 2 multiplying because of this difference, 3 multiplying because of this difference, and on the right it's the same but negative, -1, -2, -3. So here we had 3 on each side, and so it was a nice 3 and 3, but it's the same. If you have 1 on one side and 5 on the other, you can do the calculation. This one will be 1 times 2 times 3 times 5, and this one only up to 1. So basically you get a product of factorials, right? On the right you have to count whether it's odd or even to add a minus sign because of the multiplication, but you can do it all one if you have pre-computed the factorials. For example, if you wanted to compute this mod p, well, you need the inverse of the factorials mod p, which you can actually compute in linear time. If you're lazy, you can do it n log n time, typically not a problem. So yeah, with that you will be able to compute this very fast. All you need is to pre-compute the factorials, which luckily can actually be done. The factorials up to n, up to the degree of the polynomial. So yeah, I think this is a very nice trick to know. All of these different versions, I wanted to share it. Well, now I want to quickly mention linear recursions. What is a linear recursion? You probably know this already. When you have a function, and basically it's like Fibonacci. Maybe you have fn could be Fibonacci. Well, Fibonacci is defined as the sum of the two previous values. Well, you can think of any linear recursion where you have a combination of the previous values. Here I have an example of 3 previous values. My function is basically the a times the previous value plus b times the second previous value plus c times the 3 values behind. And there is a general procedure in order to solve this in complexity. Well, if the linear recursion has d terms in total, then there is an algorithm of complexity d cube times log n in order to compute the nth value of this recursion, which when d is very small is okay because basically log n is all you care about, but for a large recursion it might be problematic. And what is the algorithm? Well, the algorithm is like this. Basically, you create a matrix and you use a trick like this, that your matrix can transform from 3 consecutive values, or in general d consecutive values of the function, to another d consecutive values, but one step forward. Well, that's easy because for all values except the last one, you just can read the next one, and that's so easy. So you put that in the matrix, you read the next one. And for the last one, well, you have exactly the d previous values you need, and you can write here the linear combination. So this row will tell you exactly what the recursion is. And well, because of how this matrix is defined, a trick is that you basically know the characteristic polynomial of this matrix. If you call it x, the matrix, the characteristic polynomial will always be that given directly by the recursion. So here it is like x cubed, because we have the 3 here, minus this a times x squared minus bx minus cx. Oh no, sorry, c, because this is like plus 0, so x to the 0, 1. This always holds. This has to be the characteristic polynomial of this matrix. But we don't care about the characteristic polynomial. Actually, all that we care is that this is 0, which always holds for the characteristic polynomial. But without calculation, you can check that this makes sense, because the matrix applied 3 times shift the function 3 times. If you apply it 2 times, it shifts 2 times. So if you make this shift, like you're aligning and summing in such a way that the equation perfectly aligns, and so it has to be 0. So don't care about characteristic polynomial. There we have a concrete reason in our specific case why this must be 0. So we can use that as an axiom directly. Once we know this is 0, we can use it to our advantage, because the method for computing linear recurrences is typically to compute a to the power of n quickly, because basically since multiplying by a advances 1 step, if you want to go to the nth step, you need to multiply by a n times, and you can do it efficiently by logarithmic exponentiation, right? but the cost of multiplying two matrices is typically d cubed, so it's very expensive. Even by doing Strassen or some efficient thing, you get like 2.7, not very good, not much smaller. We want to do better. And the trick is that you can think of this as a polynomial. You want to compute x to the n, but modulo this polynomial. So you can do an equation of polynomials. You want this polynomial x to the n mod that special polynomial of the recurrence p. Why? Well, because this is the remainder, basically, so that means that x to the n will be p times q for some q plus the remainder that you're computing, this thing, the remainder. Well, then when you actually place a here, which is what you are interested in, you know that p evaluated at a is 0 because it satisfies the recursion, is what we know from before. So for our matrix, that means that all that remains is this R, which is exactly this. But the good thing is that this can be computed much faster because this is just polynomial computations. We can just work with polynomials. Of course, this is multiplying of polynomials and computing everything modulo this polynomial. So you probably need a polynomial division for this algorithm to work. But doing it naively, still you can do it in d squared time, which is already immediately better than matrix multiplication. And you can take advantage of FFT, basically, to quickly compute a multiplication of two polynomials mod p, where p you cannot choose it. It's a polynomial and it's the polynomial of the recurrence. But this is something that you can do using FFT. You multiply your polynomials and then you divide, and you can divide with FFT. So all of this can be done in the same asymptotic complexity of 1 FFT. Maybe you have to do like 8 FFT, I don't know, but the asymptotic complexity is the same. And FFT gets like n log n, so d log d here. So this is much better and much faster than the basic one, which is closer to d cube. So you have to know this trick. You might need it. At least the very basic d squared is already a massive improvement without FFT. And if you put on top an FFT, this is much faster than the basic one without taking anything into account. So if you ever need to solve a recurrence requiring many previous terms, you should know that this is a much faster way than the most basic matrix one. Okay, and now last but not least, the final theme is block moving, the block moving idea, like I call it. Okay, but first of all, I encourage you to think about this problem if you don't know it already, how to solve it. I encourage you, if you have time, to pause the video after hearing the statement and trying to solve this problem, and then later check the idea. Because it will be much more interesting if you try to solve it beforehand. You will appreciate the idea more. If you don't know it, maybe you already know the problem and can solve this. The problem is like this. Imagine that these are buckets of water and they have a maximum capacity, so they can each hold 10 liters of water, say, but L is given in the problem. You're required to empty all of them, and to empty, you throw them to the right. So here is an infinite bucket where you can empty, but the only possible move is to pick one bucket and put all of its content on the one on the right. So in one move, and you want to do it in the minimum possible number of moves. So sounds simple. You basically try to move everything to the right. So in one move, you can, for example, put all of these 5 into this one, and so this becomes 9. Okay, good, and now this one has 0. Okay, you could easily continue like this, but you have a problem. See, if there is a maximum capacity, if, for example, you choose to move this 9, well, on the right, it already has 8, so at most 2 can be moved. So you will get 7, and this one will become 10. And you still have already used 2 movements, right? I could continue like, okay, now this 10 I will move it here, one more movement, I will move this 9, why not? Okay, that will be one movement. Okay, Well, but then what is the minimum number of movements that I have to make? And ideally, for bonus points, give me a sequence or give me an algorithm that is explain me be able to solve the problem, or at least give me a winning move. Give me one initial possible move that is correct, that leads to an optimal solution. I will leave this here for you to think about it, and I encourage you to pause right now and think about it as hard as you can, and then continue watching, because the knowing the ideas that I will show next will help a lot with this problem, and well, you will have a higher appreciation if you think about this one and you don't solve it, and then you see with the ideas and say, oh wow, I should take this into account in this kind of problems. Okay, without I won't delay it further. Okay, let's start with the block moving idea. And first, I will keep that problem in the back of our minds and go to another different problem, which is very well known. Let's suppose that we have a certain number of blocks on each cell of an array, no matter how many, and we have a target distribution, right? In principle, of the same number of blocks, so that it is possible, right? So for example, the target distribution is 4 in every cell, I don't know, but this one has to have 10 and this one too, I don't know. So this should have the same sum. I didn't check, so probably the sum is very different, but let's say this one has sum 37 and this one has 37. Okay, that's okay, because if they have a different total of blocks, then obviously it's impossible. If they have the same, okay, you can move them around and get to this configuration, but you want to do it in the minimum possible number of movements. And what is a movement? Well, I will define a movement as picking one of the blocks. Okay, these are numbers now, but you can imagine, for example, here it says 4, so inside here there are actually 4 blocks. And the operation is to take one of these blocks and move it one to the right or one to the left, and that it costs 1. So 1 is the cost of moving one block, one cell, adjacent cell. You cannot move it far away. You have to move it adjacent. That's the rule, right? So I want the minimum cost to achieve the final destination configuration. So I call it the block moving idea, basically because this is a language I use for more elementary audiences. This is friendlier, basically, for high school students, for example, and such. But you're well finalist, so I assume that I can call the idea by the proper mathematical name. And basically what I'm using in this kind of problems is flow-cut duality. Flow and cut, actually max flow and min cut, but flows and cuts in general are super related, and there's a duality between them. And that's what I exploit in this kind of problems. Flow is a very general concept. Maybe you're used to see it mostly as a black box algorithm where you have to compute a flow actually, and you say, okay, it's a flow problem. I build the network, I create a graph, and then I run the code. But flow is a very useful concept by itself. Maybe you have a problem where you never run a flow algorithm, never. You don't run for Recursion, you don't run DNITs, you don't do a flow algorithm, but you use flow anyway. I think we already had one like that in Planarity, where we used a flow to compute something, but in a very nice way, but there was no flow algorithm actually running. And that is a common pattern, because a flow is a very general concept. Basically, any time that you have any blocks, it could be blocks, it could be cars, it could be liters of water, it could be anything that flows and does not get created or destroyed, or if it gets created or destroyed, at least it is created or destroyed in a controlled way, so that we know where it is created and how, so that we can keep track of it. But basically it moves, and if it is created or destroyed, we know how. We can count it. Otherwise, we have no idea what's going on. And well, basically, yeah, you can always think of it in a graph, but it is very useful even in very simple graph, like a path. Here, our graph is a path. We have a path, that's it. We can only move to the adjacent ones. And well, if you observe carefully, the blocks here that I defined are basically a flow. They are units of flow, and the operation is to make them flow. Okay, I already start with 6 of flow here, I start with 7 of flow here. Maybe you're used to the standard algorithm that has a single source, so well, you can imagine that there are imaginary arrows sending this immediate flow to this one. But more in general, for flow, you can imagine that each node has its own value and it can create or absorb, but it is a well-defined value. And here it is like that. Each node has this amount in the start, but we'll have to have a certain amount in the end. And we can use that to our advantage because we know that there will be movement. That is a flow. A flow is basically choosing how much moves through each edge in the graph. Choose where the movements are. And once you have a flow, once you define where things move, once you've chosen what moves where, that determines the net outflow and the net inflow to each node, which in a normal classical flow problem network, you ask for conservation of flow. So in each intermediate node, the outflow, the net flow out or in should be 0. The same that enters must leave. And the exception is S and T, because basically the net outflow summed through all the nodes always will be 0 for any graph. Because each edge moves, adds inflow here, but removes, but adds outflow here, right? So yeah, in the classical networks with one source and one sink, well, all the outflow is here and all the inflow is here. But more in general, we can have any configuration that we need. And we can actually check that here, for example, well, this node starts with 4 and must end with 4. So for the chain of movement that we do, whatever we take out must eventually be brought back in order to keep that number of 4. So this one has flow conservation. But for example, this one starts with 9 and has to end with 2. So this one requires -7. This one requires well, it depends if we count outflow or inflow, right? But let's assume we count outflow. This one will have 7 outflow. It has to lose 7 blocks, right? And this one, on the other hand, has -2. It has 2 inflow. It needs to receive 2 blocks, right? Okay, these values should add up to 0, as I said, because otherwise it means that the ending has a different number of blocks, so they should not only be moved, but also created or brought from outside, something like that, so it will not be possible. And well, the key idea, of course, now that we can think of this as flows, is, okay, we know of cuts. And in any graph, if you take a cut, like you divide the nodes in 2 parts, and you consider the edges that cross, that's the only way to move flow from one side to the other. So basically, all the flow going from this set to this set must cross these edges. And you can actually, so you can zoom the net flow in that direction. Let's say you can fix a direction. You can count the net flow in that direction by looking at the cut edges. But there is also another way to compute it, which is looking at the sum of all the nodes in the set and computing the outflow. That is the total outflow that will go to that region, right? And well, in this kind of problems where you have a line, it's especially nice because basically, what is a nice cut to us? Well, this, a line, a cut, the left and the right, that's it. And we can easily know how much outflow we must have. For example, okay, this one requires to get 1 and this one has 1 more, so 1 has to go out. So we can do prefix sum and check that here in total net we need to get 2. So -2 is the net total. So that means that in this edge, well, through this cut, in total we will need to bring 2. It is necessary. The net flow crossing here has to be -2 at the end. There's no other way because in total, checking how much we need for this one and how much we have to go. Well, this one has 1 extra, but this one has 1 minus, and this one needs 2. So 2 have to come. And luckily, in a path, it's very nice because there is only 1 edge here. No, so basically, this says that when we consider this edge and look at how many boxes cross it, well, the net flow through that edge must be 2 in that direction. So basically we don't have too many options. We can send 2 in that direction, and that's all our flow. Or well, there are other solutions. There are other ways to create a 2 net flow that way. We can send 3 that way and 1 this way. We can also create 4. We can send 4 that way and 2 this way. But basically for this problem, it is quite easy to convince yourself that these solutions correspond to movements and shuffling around things that will not be optimal, because you could have avoided doing that. For example, if you at some point move a box like that way, and later at some point move a box here, you could instead of bringing this box, you could do the same, and when the box that would have come later arrived here, you say, okay, I avoid moving them, because it's like I imagine that I swap them, but I don't do, right? So basically, yeah, you can say that the optimum is doing that. And this gives you an optimal solution already. You can compute the minimum number of movements just looking at each cut and seeing how much must cross the cut, because that is just taking the absolute value of the prefix sum there. So the code is super efficient, super clear, easy, right? And the idea was really simple, just noticing, okay, this is a flow, this is things moving, because that is actually a flow, things that move from one place to another. And then let's check the cut, because a cut is a very nice thing, right? So very intuitive but very powerful idea. This actually appeared in one of Fidel's contests. I didn't prepare for this. Fidel chose that problem by himself, but now thinking about it, Fidel had a problem in one contest where, well, there was a tree, and you had to select a node in order to move everyone to that tree, to that node, and such that the total movement is minimum, right? But okay, you can consider cuts, and well, the most obvious cuts in a tree are edges, because of the property of a tree, an edge cuts the graph in two, and that edge is the only way to cross from one to another. That's very nice of trees. So if you consider an edge as a cut, you can think, okay, how many nodes are on this side? Let's say, well, this is like the median edge, right? Oh no, 5. How many nodes are on the other side? 4. So I don't know where the optimal node I will put. Maybe I put it on that side, maybe I put it on this side. But if I put it on this side, then all these 5 nodes will have to cross this edge, right? So at least when I consider the edges movements, the movements corresponding to this edge, because okay, in this problem also basically we are moving things, so we basically want to create a flow going to a single node. So the question is what node to choose and what cost it has. I think only the cost we needed, so it was easier. What cost would it have to make a flow to the node that it's cheaper to send everything? But doing the same idea of checking the cuts, okay, if we choose one in this side, 5 nodes, all of these ones will have to cross this edge, and we choose one on the other side, then all of these 4 will have to cross that way. So it is obvious that for each edge, if the edge has A on one side and B on the other, at the very least for that edge, and only looking at that edge, the number of movements that have to occur through this edge alone is the minimum of A and B. So at the very least, the cost has to be the sum over odd edges of the minimum of, well, let's call it edge A and edge B, right? If you go through all edges and compute this number, how many nodes are on each side of the edge, at the very least, this is a bound. You cannot get less than this. And it's not too hard to convince yourself that this is actually the answer. This was a bound, and it was very easy to achieve by just thinking in terms of, okay, let's look at a cut, because we are moving things around, and when we move things around, it's a flow and cut are dual. But this is the actual answer, so this gives a very neat implementation too. You just do normal DFS, count the number of nodes in the subtree. So if you have x below, you have n minus x above the edge. And so you take the minimum and sum it to a global accumulator. When you sum over all edges, that's the answer. Super easy. If you know maybe you solve this problem by using centroid, because actually it can be proved that the centroid is the optimum point, but maybe you don't know why. Well, basically, it's not too hard to prove that the centroid actually achieves this bound. So now we have a proof. You have to check that the centroid achieves this bound, and well, this cannot be improved, so the centroid is optimal. So yeah, we already see that this is a powerful idea. And just to finish, I will apply this powerful idea to our original problem, which I think it's quite tricky, and I don't think it can ever be found the solution if you don't apply this trick. Here, there is definitely some kind of flow. There is a strange rule. It's not like the cost. The cost is not the cost of a normal flow, because it moves in steps, and there are discrete steps. And there is the rule that we cannot go over 10 at any time, and we don't care about the movement of each unit, but only the number of steps. So that's weird, but still there is flow moving, right? And it's in discrete steps with some rules, but there is flow moving. So maybe using that is enough to see that cuts might help, and they do. Let's consider this cut, for example. How much flow is on the left of this cut? Well, 8. There are 8 units that I have to send to the right. Well, at some point, those 8 units will have to cross this edge, right? And how much can I cross on one single step? Well, at most 10. There is no way to send more than 10 in a single step. That's obvious, because you can, at the the optimum would be that you have 10 and the recipient has 0 and you send everything, but never more than 10. So basically that says that, okay, maybe I can pass all of these 8 units on the left to the right of this cut in a single step, but at the very least I need one. So this cut will, so here movements of this step, at least there will be one. Now when I consider this cut, for example, this other one, now the situation is different, because the total is 17. And I cannot send 17 units in one single step because of the rule of this problem. I need at least 2, because that's the capacity of a single bucket. So at the very least, I can already prove that doing this move, I will need 2 of this move at the very least in the whole problem, because otherwise this flow will not be able to cross this cut, right? I mean, basically, we go through each cut and just check how much flow on the left will eventually cross, and optimistically we can assume that it always crosses in optimal steps of L, and we won't be able to go below that. And well, similar to what happened here, amazingly we can it can be proved that that value is achievable. So actually it is the answer. The optimal is to just look at each cut, make the prefix sum to see how much you must send, and divide that by L, take the ceiling, right? And sum all of that. And that is the number of movements that you will, well, you obviously need that, and you can achieve that, right? And if you believe that you can achieve that without proof, which can be done, it's a nice exercise. But basically, if you believe it, it's also not too hard to now give an algorithm that makes an optimal move, at least the very first optimal move, because you just have to check whether a certain move changes this number. I mean, the magical number will be sum over from I to 1 to n of the prefix sum at I, which considers all of the previous, divided by L ceiling. Basically, this summation gives the answer. So you have to make a move checking that the change in this summation, right, which only changes 2 values, right, when you move, or only 1, I think, yeah, when you move from this to this, this cut won't change, this cut won't change because the total on the left is the same. You only change the number for this cut, right? So you have to check that you make a move that basically reduces the number corresponding to that cut, right? Like the total flow on the left, once you send, should cross this L barrier so that the ceiling decreases. As long as you do that, well, the number will have decreased at least in 1, And of course, you wasted one move, so everything cancels out, but that move is optimal. If you make a move that does not decrease the value, well, it was wrong. That was not optimal. So that's it. Okay, the final proof is tricky, but the idea is so simple, and it's so immediate to see that this is a bound and you cannot go below this. And if you do some examples and see that you cannot, it seems that you always can, you will submit it. You will say, okay, let's try this value, and it is correct. So, well, I hope that I convinced you that this is a very nice and very powerful idea that you should have always in the back of your mind. That basically finishes everything. We managed to see all mixed topics, and well, this has been my final lecture. I hope that you enjoyed all the contests and all the lectures, and that you enjoy the final contest, because you should be seeing this lecture at the very least before the final contest. But maybe you're watching it after all the contests. That was not the idea, but you can. I hope you enjoyed both my lectures and my contest. I'm very happy to have been invited to this event, to the Brazilian summer school this time. So I want to thank especially Rafael, who contacted me and invited me and everything, and helped me a lot to make all of this possible. So I feel very, very happy to have this possibility, and hope you. I want to wish you a lot of luck in all the contests that you do, and keep practicing. That's it. I hope you had a great time. See you.